Hello everyone. Welcome to our RIA Market Trends webinar series. Today's webinar is entitled The Revolution of Robotic Offline Programming. Thank you for joining us today. My name is Clarissa Carvalho and I'm the Marketing Specialist for the Association for Advancing Automation. I'll be serving as your moderator today. Attendees that have joined this webinar today have joined in listen-only mode, which means that you are muted. If you have questions during the webinar, please submit them in the questions box in the control panel at the right of your screen. This webinar will be recorded and a link will be sent to you within the next 24 hours. I would like to thank our exclusive sponsor of today's webinar. RobotMaster is a leading CAD/CAM-based offline robot programming software, which provides quick and easy programming tools for multiple applications, saving time and money while maximizing return on investment. RobotMaster delivers an unmatched offline programming capability for robots, easy programming of precise robot motion, and quick generation of trajectories of any size, with minimal programmer intervention. Their strong background in CAD/CAM software has enabled them to bring a revolutionary approach to programming industrial robots. Thank you to RobotMaster for sharing their time and expertise with our RIA community. I would now like to introduce our presenters today. Corey John studied at the University of Minnesota and started his professional career in 2007. After spending 10 years working in CAD/CAM software sales and support, Corey transitioned into robotic offline programming software in 2017 when he joined the RobotMaster software team. Since then, he's been working with robot manufacturers, integrators, and robot programmers to help make robotic offline programming easier and attainable to the masses. Greg Culp is a mechanical engineer from Temple University. He started his professional career in 1997 as a CAD/CAM software application engineer. After 10 years working in CAD/CAM software sales and support, he transitioned into robotic offline programming software. Since 2007, Greg has dedicated his career to the evolving needs of robotic programming and collaborating with robot manufacturers and integrators for the greater adoption of robots in industrial manufacturing. Thank you, Greg and Corey, for joining us today, and I will now hand the presentation over to you.
Thank you, Clarissa. As she said, my name is Corey John, and I'm one of the software sales managers here with Hypertherm and the RobotMaster product. I first wanted to give a quick overview of who we are and why we have some authority on presenting the revolution of robotic programming. RobotMaster started almost 19 years ago in 2001 and have been dedicated to the offline robotic programming market ever since. In 2015, Hypertherm, a company with over 50 years of experience in the manufacturing space, acquired the RobotMaster product. Hypertherm is globally headquartered in the United States with over 2,000 employees worldwide and are on 6 out of 7 continents. One of the things that we are most proud of here is our ESOP, as we're a 100% employee-owned company.
Hello, my name is Greg Culp, and I'm a Senior Software Sales Manager at Hypertherm Incorporated, RobotMaster Software. Our goal in this presentation is to highlight how offline robotic programming has evolved over the years. What this chart represents is starting with manual teach pendant, which is how robots were initially programmed in the beginning. The operator is teaching the robot what to do, and the process is online. The method of programming is still used today for many applications. When you look at the chart, I do not want to imply that things are getting better as you move from left to right. Do not look at the chart as the column on the right is superior to the column on the left. What the chart is showing is the progression of the technology and how it has advanced over the years. As robots migrated into other applications, so did the need for software. Again, teach pendant programming may be the best solution for your application. So the chart indicates how robotics and software have advanced over the years.
Since the beginning of robotics in the manufacturing space, the manual teach pendant has been a prominent player when it comes to programming and is still widely used in today's robotic market. Just like everything, there can be several advantages and disadvantages when programming in this way. As I stated earlier, the manual teach pendant is still widely used in today's market. making it easier to find people that have a baseline understanding of this method of programming. Manual teach pennant is a highly flexible method of programming and can be beneficial for simple applications such as pick and place and material handling. Because of the flexibility of the manual teach pennant, it has allowed robotics to be used in a wide array of applications. Moreover, since the robot is being programmed online, the need to have an accurate robot tool center point or user frame is not an issue. Just like anything else, every advantage comes with drawbacks. One of the major obstacles with online programming with the manual teach pennant is every time you need to create a new program or touch up an old program, you need to take your robot out of production, costing the company revenue. Because of this flexibility nature of the manual teach pennant, the downside is speed. Complex programs can take days, if not weeks, to program. From our point earlier, these days or weeks of programming time can cost the company revenue as the robot is not creating new parts. When creating programs that require higher accuracy, this method of programming is only as good and as accurate as the programmer's eye. Also, since this is a manual process, there's no ability to alert the user of upcoming robotic errors, and it's still time-consuming to fix any of these robotic errors you have created. Just like any revolution, progress is made with a single step, and we saw this with the creation of offline emulators. The emulator allowed the customer to keep their robot in production as you were creating the program. Even though this was a big jump in manufacturing productivity, keeping the robot in production, this is still a very manual process. The emulator is essentially just a manual teach pennant behind a computer screen. You still had all the flexibility that came with the teach pennant programming, but also got some of the same drawbacks, such as accuracy issues, as your program is only as good as the person's eye. Since there's no intuitive method in this programming, people still are spending much of their time manually fixing robotic errors and needed someone who is well-versed in robotic programming to complete this task. One of the things that propelled the robotic programming market forward is the shift from low mix and high volume to high mix and low volume. No longer are the days where robots are mostly used in situations where we'll be doing the same things hundreds of thousands of times, but the shift to using them for runs of 1, 10, maybe even hundreds. This made the need for faster programming even more crucial. When you are going to run the same part for a year and you're going to make 600,000 parts, it doesn't really matter if it takes you a few weeks or a month to hand program it. You still have an ROI to use the robot. Now take that same timeline for programming a run of 10 and the robot is no longer profitable. This led to the first generation of offline programming software. Now, as robotic applications progressed and got more complex, people started to push for a simulation environment that could interact with a CAD model. With the introduction of the first generation of offline programming, this allowed you to do just that. Now you had the ability to interact with your CAD model inside the simulation, enabling you now to snap a point on the model and follow the exact edge, not deviating from it because you were using your eye. Once again, this method of programming sped up the process and kept the robot in production. This new approach was also more accurate than the emulator and teach pennant. Even though this was a big step forward in robotic programming, it was still very time-consuming. The user was still doing point-by-point programming on the part and needed lots of back and forth between the offline programming software and the robot. There were still no alerts for the robotic errors, and you still needed to be pretty well versed in robotic programming to use the software. The next logical step in the evolution of robotic programming was asking the question, if I can interact with the CAD model to create points on a part, why can't I use the offline programming software to create the robotic path off an edge of the part? This second generation of offline programming software allows the user to grab the edge of the part using all the information that's already in the CAD model to get all the correct tool vectors to make the program much more straightforward and a lot more accurate. Even though this generation of programming was a giant leap forward in time savings, it still was lacking a lot of capabilities to get an error-free program. There were still no kinematic checkers or solvers and not much in the way of collision warnings. Like we talked about before, anytime you gain speed of programming, the cost is flexibility. These second generation offline programming software sped up the programming time for edge following applications such as trimming and deburring, but the constraint of programming off an edge cut back the total amount of applications this style of programming could do.
As we all know, there has been a lot of advancements in manufacturing over the years, and several companies are putting these processes in place. flexible automation is a topic I would like to focus on, and software plays a pivotal role in this. We have been able to automate repetitive tasks like material handling and palletizing applications, but companies are struggling with automating the high-mix, low-volume applications. As of today, software is constantly being developed, and features like AI and machine learning are being implemented to help handle flexible automation. These are the industry drivers that drove the robotic market into the next revolution of programming. There became a point when companies had several CNC machines in use, and they were starting to implement more and more robots, not just for material handling applications. Applications such as water jet cutting, trimming, robotic welding cells were being installed, and people started thinking, why can't we use our CAD/CAM software to program the robot? And this is where you started seeing some overlap between CAD/CAM software and OLP software. The main difference between using CAD/CAM software for CNC machines and robots is CNC machines are straightforward or a closed-loop environment. And when it comes time to programming your robot, there are a lot of challenges, like singularities, reach, joint limits, and so on, which are not intuitive to identify or solve. Robots are more flexible than CNC machines, and this is a positive. But with flexibility comes more challenges, and those challenges needed a higher level of expertise in robotics. So how this worked: in the early days with CAM software, you would create a point file. You would then take those points and read them into a point converter, which would create 6-axis robot code. You would take the robot code, run it through a simulator to figure out your errors. This was a lengthy process and took a lot of debugging to get the robot cell running. Keep in mind, you needed a lot of expertise in robotics to make this work. After the CAD/CAM point converter approach of programming, the software transitioned into true robotic programming solution. When looking at robotic software, there should be several factors that come into play. Your software should be robot neutral, ability to work with many robot manufacturers in the industry. The software should be not designed for a CAD/CAM expert or for a robotic expert. It should be designed around the process expert. If you understand your process, then programming the robot should be easy. You need the ability to move quickly from your task environment into your robot cell environment. Being able to create multiple tasks on a part is critical. In this video, it is showing automated part selection on a CAD model. Take notice of the graphical feedback from the software to the operator, having the ability to order your path to reduce cycle time. Once the path is created, you should be able to transition quickly into your device environment, simulating your robot to find out if you have any robotic issues or if it is good to go. Being able to manipulate your data for start point, cut direction, entry, exit, and so on is also important. You will notice graphical feedback right away. Path pre-processing lets you know there is an issue. Not being a robot expert, but a process expert helps understand the issues. Features like inverse kinematics and engineering tools like workspace analysis help evaluate the robot cell with the part, and also having the ability to resolve your robotic issues and path corrections for an error-free program. These software tools are revolutionizing how robots are programmed today. So what you are now seeing is a collision between the torch and the part. In the past, the operator would go back to his parameters and start changing the data. Having a powerful interface and graphical transition tools, the operator can work directly within the robot environment to fix any of his issues that he's having for an error-free program. And lastly, we should be looking for process-specific parameters for your application. Let's take welding, for example. Being able to input weld schedules, weaving parameters, seam tracking, and other commands determine if your software is a good fit for you and your application. So let's recap. You now have a timeline of how software has enhanced over the years as robotic technology has enhanced. Offline programming software is another tool in the toolbox. When it comes to getting your job done, there are many factors that go into true robotic offline programming solutions. The software should take into consideration the process expert. The software should not be geared to the robotic expert. You should be looking for intuitive graphical feedback. When you have an issue, you want to be informed of that issue right away, and the software should recommend solutions on how to fix those issues. And the last thing you should be looking for is process-specific parameters for your application. The bottom line, your software needs to be flexible. A partial solution is not going to get your part programmed. I'd like to make a point that simulation software is not robotic offline programming software. I am not saying simulation software is not needed in the process. It definitely serves a purpose when it comes to robotic applications. When programming your robot cell for a specific task, you should be looking for key components like CAD/CAM tools, mathematical path optimization, inverse kinematics, simulation, and flexibility. These are the core components that make up a true offline programming solution. Corey and I and the entire Robot Master team would like to thank Clarissa and the RIA staff for everything that they do. None of this would be possible without them.
Thank you, Greg and Corey, for that insightful presentation. To our live attendee listeners, please submit any questions you may have using the questions panel at the right of your screen. A few questions have already been submitted, so Greg and Corey, here's your first question. I work with several robot brands. Is there a software out there that can work with multiple different brands?
Yeah, I can take this one, Greg. So yeah, as we stated before, when you're looking for a true offline programming software, you want to make sure that software can work with several different brands. You don't want to have a different software for each of the different robots out on your floor. So you want one constant programming software. And as we talked about before in our thing, separating the task from the process, the ability to program them separately allows you to be able to move parts between cells with different robots. So making it a lot easier for you. So yes, Robot Master is one of those softwares that works with multiple different robotic brands. And we can help answer any other questions that you have.
Thank you, Corey. The second question is, we do most of our programming with dependent. So what is involved in moving to an OLP software?
Yeah, I'll take this. Well, there's several benefits of using offline programming. The first thing I can think of is offline programming is going to allow your robot to stay in production. So if you're doing high mix, low volume, it'll keep your robot running, which is also going to help with cost and time of getting parts done. The second thing is you'll be able to evaluate your robot cell with the part. Doing any engineering that you need to do, you will be able to uncover issues. There may be a fixture or a clamp that's in the way. So you want to find those out beforehand instead of finding out at the robot cell, and then you have to start doing some re-engineering of the system.
Thanks, Greg. And this will be our last question. What benefits do customers see when moving to an offline programming software?
Yeah, I think following up what Greg just said, I mean, the main thing is one, keeping your robot in production. So when you're programming, the robot's still making parts and making the company revenue. Secondly, obviously, you'll know right away when you bring your part into your offline programming system that is, where I have my part in its position, can my robot work? Will it reach? Will it have any collisions? Will it have any singularity, stuff like that? So really, it's about the speed of programming, the flexibility of the programming, and keeping your robot in production while you do that. I think those are some of the major benefits.
Thank you, Corey, and thank you, Greg, for the insightful answers. And thank you to those who submitted questions. If your question was not addressed during the live session, we will respond via email. Please join us for our next webinar on October 17th, Anatomy of a Robot. Do you ever wonder what exactly is in a robot? Why do they work and why they work so well? What about the motors, control mechanisms, cables, hardware, and software? Register for free at www.robotics.org to find out. Did you know that the RIA webinars are recorded and available on the archived webinar page? Check out our past webinar recordings for free at www.robotics.org/webinar-archives. The RIA has several upcoming events, including the International Robot Safety Conference on October 15th through the 17th in Indiana, and the Collaborative Robots Advanced Vision and AI Conference on November 12th through the 13th in California. Learn more and register at www.robotics.org/upcoming-events. I hope you found this webinar interesting and informative. If you have any questions about RIA events and activities, please reach out to Corey, Greg, or myself using the contact information you see on the screen. As a reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. Be sure to visit robotics.org for a list of our upcoming events and webinars, and I hope you join us again for our ongoing and exciting series of 2019 Market Trends webinars. Thanks again, everyone, for all your support. Have a wonderful day.